still see my phone. No, the screen. So last week at least we introduced just we spoke a few things. So we want to look at the the problem that if I let the phone sit down, then you so what is the purpose of this course? But so these are too tiny. Can you see what I'm writing? I think here we're just wasting. This will be wasting time. It writes two things. But so my Chrome is starting. Maybe let us see if it will accept. So let me start it. This one is just looking it up.
If it fails to work, I suggest or rather request you can give us a brief introduction of the course outline and what we are going to cover, then we call each other.
Yeah, so if it starts, so basically the purpose of this course is to help you develop skills just in numerical differentiation and curve fitting. That's the purpose of this course, is to help you develop skills in numerical differentiation and numerical differentiation, integration, and curve fitting. And so what are the expectations, or what do we expect by the end of this course? Some of the things you are supposed to cover. I don't know if you are writing them down. So the expectation is that by the end of this course, you should select and apply appropriate numerical computation technique for a given application. So whenever you are given a specific application, you are supposed to choose and apply a suitable numerical technique. So we will learn, basically, we are just looking at the numerical techniques. We will look at solving systems of linear equations using the matrix methods. We want to generalize this because that is the basis for everything. And then, having looked at this, we will look at curve fitting. Basically, that if you are given a data, can you define a mathematical representation of that data? Can you get a function that defines that data? And then we shall look at ordinary differential equations and look at the numerical implementation. How can you solve them numerically? So that's why I'm saying that, one, the expectation is that by the end of this course, you should be able to select and apply appropriate numerical computational technique for a given application. Is that okay?
Yes.
Yeah. And then the second one is that you should be able to drive a suitable functional model for a given set of data. That if I give you a set of data points, you should be able basically to find a mathematical representation of that data set. Or you should drive a function that describes that data set. And 3 is that given some of these techniques, we see that we look at a different number of numerical methods. And so basically the other expectation is that you should be able to develop and apply an appropriate computational algorithm for a given application. So I see, for example, we will learn different ways of solving, for example, system of linear equations. And so given the way, can you develop an algorithm which can implement that particular method on a computer or in any system? So that's what I'm saying, that one application, the last one expectation is what? Is that you be able to develop and apply an appropriate computational algorithm for a given application for use in a computer. So everything before we think of implementing, what we will try to learn basically, that you need to understand the background, understand the method. Once understand the method, try to implement it. Well, first of all, come up with an algorithm that can help you implement. And once you develop an algorithm, and then you can now implement the algorithm you come up with. So that is what happens. You develop or understand a method, develop an algorithm, and having developed an algorithm, you now implement the algorithm. So that's one of the expectations of this course. And now, having seen the expectations, what is the course outline? So the course outline is that, one, we will look at interpolation. So what interpolation means is that given a set of data points, you are able to find a function that can define the value of, I don't know how I put it. But so what I'm trying to say is, given a set of data points at some given points or defined points, you are able to predefine or try to predict the value at the intermediate points. So if the data is given, for example, at the value 1, 2, 3, then you can define the value of that data at the point, for example, 1.15. So that's what we are saying interpolation. So I want to stop sharing the screen, and then the laptop is back. Let's hope it will behave. So first of all, I'm not getting off the phone until the screen has been shared and is working correctly. So can you confirm that you can see my screen?
Yes, you can see the screen, but this is a simultaneous question.
So if I animate, so if I unmute the phone, can you confirm that you hear me? No, I muted the phone, so I'm using the laptop. Can you confirm that you can hear me?
Yes, you can.
Okay, yeah, that's perfect. So this technology can misbehave at the right time and the wrong time. So we have seen the expectation and the purpose of this course. So I'm now going to give you the course outline. So what is the course content? So later on, at the end of, maybe in the middle of the semester, I'll just basically produce a PDF of these notes and then I send to you. But also I try to give you some textbook that you can use for this course. So I said one, we will look at interpolation. So interpolation, you are just said is basically trying to predefine or try to predict the values at which or in the middle of the data points. That's what we mean by the interpolation. And for us to look at this, we shall first define what is called the finite differences. And then based on this, we find what is called what? An interpolating polynomial. Based on finite differences. So when you have these finite differences, we define the polynomial, which is based on the finite differences that we will have looked at. And also, we shall define what is called what? The Lagrange interpolation. So we shall look at two main types of interpolation. Interpolation based on finite differences and what is called the Lagrange interpolation. And then we can see the advantage of this one and see where each one is applied. The first one is basically applied when you have the data at for safe, then you can use finite difference. While the Lagrange interpolation allows you to define the interpolation just basically on a general. You find even when you have the data points defined at steps which are not of the same size. Then two, we shall look at what is called the curve fitting. So curve fitting basically we will look at, we shall just focus on what? The least squares method. That given a set of data points, can you come up with a curve or a linear equation, if they are linear, which minimizes the distance between the curve and the data points? That's what we call the least squares method. So you find the curve such that the distance between the points on the curve and the data points is minimum. And then we shall see how to drive this and how to come up with such a curve. By first of all looking at the data and then look at how the data behaves. For example, if it behaves like an exponential function, then it means we try to fit an exponential function to the data so that we define the constants. That's what we mean by the curve fitting. Basically, you're looking for a curve that can describe the data. Then from that one, we will do what is called the numerical differentiation and integration. So basically, in class, you looked at integrating all rules of integration, no differentiation. First of all, how to differentiate a function using the power rule, if it's an exponential, the chain rule, the quotient rule, the product rule, and so on. But what happens if you have the data points or the function is only defined at specific points? Can you try to approximate the derivative of this function at some other points? And so we shall do this first of all from the first topic, because first topic we say that given a set of data points, we can approximate this or find a function that describes these data points, just interpolation. And so it means we can have a function that can describe our data points at where they are given, and also maybe try to approximate the data values at the intermediate points. So from this function, we can now differentiate the function basically. That's what we're calling what the make of differentiation. And so basically, so here we will look at derivatives from interpolating polynomials. So this topic will basically be linked to what we will have looked at. And if I don't know the approach I may combine when I'm teaching, I may just start on the interpolation and then continue with the derivatives and so on. And so after that one, we will now look at numerical integration. And so the methods we look at is one, trapezoidal method, and then we look at the Simpson rule or method, and when it is applied. And when you look at this, we can also look at other quadrature, which are called just basically the quadrature methods. So like the Newton Cotes formula or method. Because once you can describe your data using a set of polynomials, then it means you can integrate that polynomial. And the polynomials are basically very nice because they are very easy to integrate just by the power rule. That's why somewhere you saw the power series, the Taylor series, the Maclaurin series, is basically trying to approximate each of the polynomial by a each of the function by a polynomial, since they are very nice and very easy to work with. So we shall also look at what is called what? The Romberg integration. So I'm just giving you some of the things we look at, and it's not necessary that we look at all of them. Is for each of these parts, for example, in differential integration, what you need is just to show you the techniques and the concept, and then you can apply any other method using the same technique. But for the exam, I will only set what I taught. If I don't teach, for example, the Newton's Cotes method, I will not set an exam. And so here, some of these methods maybe to interpret apply some of these methods like this. We will try to just first of all just start by using Google Sheet or Excel to implement what we learn here. There is something also you can go and look at. It's called the GeoGebra that allows you can sketch a function by freehand, and then by freehand, then you can find its area. You can just go even on a computer, put your hand on the screen of the computer, and then sketch it just by the GeoGebra. Then you trace it, and once you have, and then you find the area of that your hand by implementing this method like the Simpsons, the trapezoid, using the GeoGebra, combining them. I tried to show you some of this one. Then just on so this one, just Google the GeoGebra, and then you can start playing around with GeoGebra. It does this numerical integration very well. And then later on, when you have some methods now, this is just to try to play around with them. Given time, or using the one now we said, I can try to implement just to show you how to implement some of these methods, either using one of these computational softwares, either R, Python, or MATLAB. Then we also expected to look at the numerical solution for the ODEs. you learned in the class methods of solving the ODEs, separation of variables when they are homogeneous, the integrating factor, and so on. But when you go to the real world applications, be it in engineering, be it in biology, or in other part, you get differential equations which are so complicated, very, very complicated. And so you can't integrate them using the methods we learn in class. What you need is just to approximate their solutions. And so that's why this part is very important. And so we look at a number of methods, also not all of them, but a number of them. One is we look at the Taylor's method, or just a method based on the Taylor's expansion. And then we shall look at the Euler's method. We look at some of these called the Runge-Kutta methods. We can look at also, they are called the multi-step methods, or the predictor corrector methods. And then if time allows, we can look at what? The simple boundary variable problems. So you look at a differential equations, define on some domain where you have the boundary conditions, or you are given an information on the boundary. For example, some of these things, if you go to a house now with the temperatures, so you have the temperature distribution function, which you can have the heat equation, and then you want to define what should be the temperature in the room on the walls. You can either set the flux that the change on the room on the wall should be 0, or you just assign that I want the temperature on the walls to be, for example, 10. And so those are what? When you predefine an equation and then you set values on the boundary, be it the values of the function itself or the derivatives, that's what we call a boundary value problem. Is something where the boundaries are given. So these are these are the first ones. We'll call them IVP. That is the methods of solving initial value problems. You have a differential equation that describes something, and then you are given the starting point, and then you need to approximate what will happen in a future time or in some other values. But the most important thing, the basis of all this that we look at is called the matrices and simultaneous linear equations. So when you are solving even ODE, when you are solving a PDE, then you can end up solving this as a system of linear equations. You pass from a partial differential equation, meaning depending on several variables, as a system of single or system of ordinary differential equations, which then can be passed to a further system of linear equations. So, for example, you move from a one partial differential equation depending on two variables into two system of differential equations, and then maybe into a number of linear equations that you need to solve. So basically, this forms the building blocks for most of these other things you learn from here and in the future. That's why they are very important. And here we'll basically look at least matrices, because we need to understand them. What's a matrix? What do they do? What are some of the terminologies in matrices? So that we can be able to apply them appropriately. And then methods of solving them, we will look at what are called the direct methods. So the direct methods are, for example, using the inverse method, using the Cramer's rule, LU factorization, the Gaussian elimination method, the Gauss-Jordan elimination method, and so on. And then we also look at now what I call the iterative methods. So the directive methods, they give you the exact solution in a finite number of steps. But the challenge is they are so sensitive to round-off errors. And in the daily life, there are some cases we cannot avoid errors, round-off error. So these methods are so sensitive. So when applying them, you either try to minimize the propagation of errors, or if you don't minimize, they may give you inconsistent or inaccurate results. So in short, they give exact solutions in a finite number of steps in absence of round of errors. But when you have round of errors present, then the good methods to use are what? I'll call the iterative methods. So iterative methods, this is iterative. So this is I. You start from an initial guess, and then you iteratively start generating the set of solutions until you converge to a solution or you approach a solution. And so these methods are very good because some of them are even, you can make a mistake in a step and it automatically corrects itself and then it goes back to the solution. Basically, so when I sketch, for example, you are having a set of points, you want to try to follow particular maybe a function and then see arrive at zero. So you can start with an initial guess here. You want to go here. And then when you compute, maybe the next guess comes here. The third one comes here. So it will start coming, it will find these values. So if by any chance you reach at this point and you make a mistake, and if instead of coming here, you come back to this point, this method is still able to correct itself until you come back to this. So you may just require more steps than you could have used, but provided if the method is correct, if the implementation is correct, they will still automatically correct themselves. So that's the difference between direct ones. They just give you exact solution in finite number of steps, but they are sensitive to round of errors. Iterative, they approach a particular solution, so you do it iteratively, and then with them when you find the errors, then you can approximate. Then we shall look at if time allow SOR methods, but they are just also basically the group of iterative methods. So here, what we can look at the Gaussian elimination. I'm just calling GE. We can call it the Gauss-Jordan elimination method. We will look at LU factorization, but they contain inverse method that you looked at. They also contain is what Cramer's rule, etc. So for this course, I think I may only focus on this and how those methods, for example, the Gaussian elimination method, the Gauss-Jordan and LU, they are used to finding the determinant of matrices and also finding the inverse of a matrix. If you have a very large matrix, then you cannot use the cofactor methods. So this is the course outline. From that one, do you guys have any question? Kuna mtu ako na swali ama kuna mtu mwenye ako na jibu? Kama kuna swali. So if there are no questions, at least then we can test the flavor of this course. So we can start with the first one, the first topic, matrices and simultaneous. Linear equations. So we'll just start from the basics, trying to understand matrices. What are matrices? What are some terminologies commonly used in matrices? What are some of the key terms? So that when later on we start defining using these terms, then you know what we mean. So I know you guys did this somewhere. Can somebody tell me what's a matrix? Anybody from you guys, what's a matrix? That's correct. So we can write what he said. A matrix is an array, or you can just say is a rectangular array of numbers or elements arranged in rows and columns. That's a matrix. So then we can say that the horizontal array of a matrix are called the rows, and the vertical array called the columns. So what am I saying? So for example, I have this is a matrix. I'm not putting first of all because we just say it's a rectangular array of elements or numbers. So they are not necessarily numbers. You can have a matrix of age. So if these are just a matrix of all these values, and then so we have these are the horizontal arrays, and then the vertical arrays. I can draw them in blue. So this vertical array are what I'm calling the columns, and then the horizontal array are or what I'm calling the rows of a matrix. So how do we denote matrices? So we can say that matrices are denoted by uppercase letters. Let me view and change this with, yeah, these big ones are good. So matrices are denoted by uppercase letters, while their entries by lowercase letters. So basically what we say that matrices are denoted by capital letters and these others are denoted by small letters. So if I have a matrix, I call a matrix A. If I want to mean the element of that matrix, I refer to element maybe with a smaller a. And then the next definition, what is an order of a matrix? Can somebody tell me what's the order of a matrix? Anybody in the chat, order of a matrix?
It's the number of rows and columns that a matrix has.
Yes. So the order of a matrix is the number of rows and the matrix, and it's written as the product of rows and the product of rows and columns. So we can write that a matrix, say A, is said to be of order M by N if it contains M rows and N columns. And so in generally, if we want to write a matrix, I can write, for example, a matrix in this way. So I have element 1, 1, element 1, 2, element 1, 3, until element 1n. And then element 2, 1, element 2, 2, element 2, 3, until element 2n. And then you have element M1, element M2, element M3, until element Mn. So that's how you denote a matrix. So when I write, for example, element 1, 1, I mean element on the first row and first column. Element 2, 3, it means element on the second row and element on the third column. So that's how we locate the matrix. And then I can just say this in general. The element A subscript ij is the entry at the intersection of the ith row and the jth column. So matrices can also be written in compact form, or maybe we can say is it instance notation or in tensor form. And so we can say that in compact form, matrices can also be denoted by, for example, A is equal to Aij. So I just write this Aij small one, and then with those brackets say I mean a matrix. So given, for example, this matrix, can somebody just give me any matrix? Can you give me any numbers along the row, or 3 or 4 rows? Just select numbers, random numbers from you. Let me give even 3, 2, 1. Now somebody to give me the second row. Two. The third row. 4, 6, 5. We want to add another one? Maybe for now, let me leave it this way. So the question is, what is the order of A? What is the order of this A?
3 by 4.
Yeah, so this is, we have 3 rows and 4 columns. So this is a 3 by 4 matrix. Or you can just write 3 by 4 matrix. Can somebody, for example, tell me what is the element A24?
2.
A24. We have 2 3s. So which of the two are you referring to? Let me label them as with a star, star, and star, star, star. So which of the two are you referring to?
Triple star.
Sorry?
Star, star, star.
So the one with 3 stars, right? So that's element 2. It means the second row and 4th column, and then where they intersect. So somebody could say the second row, you draw the line. The 4th column, 1, 2, 3, 4, you draw the line. So where they intersect, that gives you the element of that matrix, or the position, so the element position. And basically, when you define matrices, even using this software, you define them in the same way, and you call them using the same way. If I want, for example, I define this in, for example, MATLAB, and I want the 4th column, I just say A2, 4. Then it will give me, it will extract this element. You can go and try. If somebody is using Python, for example, Python uses these square brackets, but the Python indexing starts from 0. So this will work in MATLAB. You can try those to use MATLAB. Then it will extract the value on the second row and the 4th element. So the Python indexing starts from 0. So it will count basically this as the row number 0, and this as row number 1, this as row number 2. As MATLAB starts from indexing 1, so MATLAB will count this as row number 1, row number 2, row number 3. And so basically, if I want to get this element 2 in Python, I will say 1, and then how many is the third row, because now the third column. So this will be the 0th column, the 1th column, 2nd and 3rd. So this will be 1. So these two syntaxes, so this is applicable in Python. These two syntaxes will give you the same element too. I think also R defines this, but uses the same indexing as MATLAB. I think that's what I suspect. You can check. Also, this will work in what will work in R. So these things become very important when you are doing the programming, like you guys do programming, and whichever language you use, whichever system you use, those who use even C++, you have to understand the syntax. For example, if I'm counting the row number 1, MATLAB will count that as the first one as 1. That's the indexing value. Something like Python will count that as 0. So in R, how does it count? then those which are no's. And but so you basically call it in the same way. The first number represents the rows, the second number represents the columns. When you start implementing this, you see, if I give you assignment, for example, to program matrix and then do some manipulation from the matrix, then you will see that these syntaxes will be important, depending on the language you are using and the system you are using. Which kind of software are you guys familiar with? Which one do you use mostly in a computational computation?
We mostly use MATLAB.
MATLAB. Another one. What do you do with MATLAB? What do you do in MATLAB?
We use it. We use it for the matrices and also for modeling transfer functions, the Laplace.
Nyinyi wote sasa ni expert bwana. Ndio. Mko expert. Sasa kama mnanishinda. Is it? Na wengine wanatumia nini? Huyo mmoja amesoma MATLAB, wengine. So what I normally encourage people, even if you're not using, don't worry. It depends. So if you want to learn, then you learn. Just pick one of these. Make sure you develop that technique of programming. What are the requirements? What do I need if I'm using R and using this? Then just switching from one to another is just understanding the syntax of the other language and what are some of the key things like how do you input values. But the same knowledge of programming, the requirements, what you need, the steps will be the same in all these other. They're basically the same. So pick one which is available to you and then become an expert in that one. Just be familiar with that one fully. And then now you can, if you now later on, you can now switch to the other and start understanding this bit by bit. Any question until this point? So what is the element 5, 2 in this matrix? What's the element 5, 2 in the matrix? I don't know if I can try to open. I only shared the window, so I cannot see the screens. But that I will do the next time to try to implement some of this. What's the element A52? Yeah, does not exist. So it's basically, let me just put none, not a number. So null. Correct. Somebody typed in the chat because the matrix here has maximum 3 rows, but we are trying to access value at the row number 5, which is not there, so does not exist. So it's null. That's correct. What is the name given to a matrix with 1 column?
Column matrix.
And 1 row?
Row matrix.
Row matrix, correct. just basically a vector. So if you have a matrix with one column is called a column matrix, a column vector, and then a matrix with two columns is called with one row is called a row vector. So equality of matrices. When do we say that two matrices, for example, A and B, are equal? Because some of these terms, we will see that when you want to solve linear system of equations, we basically try to find equivalent matrices. And then so we need to know what's an equivalent matrix. So that's why you will see that I'm just repeating some of these terms so that you become familiar. That for you to solve this system, we try to drive an equivalent matrix of this, and then you'll see if you have some certain matrices, it's much easier to find the solutions or to solve for the system. So equality of, when do we say that two matrices are equal? Okay, that's correct. That two matrices, say A and B, are said to be equal. Some of these definitions will come in the exam. To be equal if they are of the same order. So that's what we say, that they have the same number of rows and columns. It means they are of the same order, and such that Aij is equal to Bij for all I and j. So that's basically what he said. So I'm just writing in a different word, but what he said, that they are said to be equal if they have the same number of rows and column, and they have the same number of corresponding entries, or equal corresponding entries. It means the entry at position 1 must be the same as entry at position 1 of B. Entry at position 10 will be the same as entry at position 10. That's what we mean. Now, can you look at some special matrices? So these are just definitions, but basically they are leading us to some of the things we need and where we will use them. So one is called a zero matrix. What's a zero matrix? Now this one, it should be quick to say. A zero matrix. Okay, yeah, correct. So a matrix A is said to be a zero matrix denoted O if Aij is equal to 0 for all ij. That's just basically what he said, but in different terms. That is just a matrix. In short, we mean is a matrix whose all entries are 0. 2. We refer to what we call a square matrix. What's a square matrix? Yeah, same number of rows and columns. So a matrix A is square if M is equal to N. Basically, because we say the order of a matrix is what? Is M by N. And so M is the rows, N is columns. So if they are equal, then say to be a square. And so if you know that a matrix, for example, is square, then the order of a matrix, just say a matrix A is of order N. You don't have to be say N by N. If it's a square matrix, then basically you don't have to mention product, just only mention one. Then 3, we have diagonal entries. What are the diagonal entries of a matrix? So you can say if a square matrix A denoted by what? By Aij of order N. No, I mean in a square matrix A of order N, comma, the entries A11, A22, A33, and so on, ANN, are called the diagonal entries, or the diagonal entries, and they form what is called the principal diagonal. Or the main diagonal. In short, in other words, the diagonal elements of a matrix are just the element A, I, or somebody can say Aij, or somebody can say are elements Aij where I is equal to J. So that's all this they mean the same definition. All elements A. If somebody asks for this definition, then just element Aii. Oh, this is supposed to be element Ajj. So in short, when this you mean is the element at the position where the row and column is the same. And so when you denote, for example, a matrix, just let us take, for example, a 3 by 3 matrix or a 2 by 2 matrix or a 4 by 4 that I have. This is the matrix. Then I have A11, A12, A13, A14, A21, A2, A31, A41, A22, A23, A24. This is A32, A42, A333, A43, A34, A44. So just this is an example of this matrix. So these elements are what I'm calling the diagonal entries. So AI, they form the diagonal entries. And this is just called is a principal diagonal. Now, having seen the diagonal, having seen what's the diagonal? What we mean diagonal entry of a matrix. So 4, what is now a diagonal matrix? Can somebody tell me what's a diagonal matrix?
It's a matrix where all elements are 0 except the elements on the diagonal.
Okay. Yeah. So it's a matrix. I can say a square matrix. And see, some of these things you have just defined them on a square matrix now because they're defined on the square matrix. So a square matrix A, which is equal to Aij, is said to be diagonal if Aij is equal to 0 for all values of I not equal to j. Is basically what he said. It's a matrix where all elements outside the diagonal element are zeros. So basically, when you have this, it means everything outside here will be zero. That's called a diagonal matrix. But it does not say that whatever lies on the diagonal cannot be zero. So this also, some of these elements, diagonal elements here, can be zero. But what you are sure is everything here is supposed to be zero. Then you don't care what goes to this line. And now, having seen the diagonal element, now we're just refining our definitions. What's identity matrix? Can somebody tell me what's an identity matrix? Yes, it's a matrix whose all diagonal elements are 1. So first we say what is a diagonal matrix. Such that Aij is equal to 1. No, not Aij. Aij is equal to 1 for all I. Yes, this is what he said, that is a matrix, diagonal matrix whose all diagonal elements are ones or are unity. It's denoted In. That to me now is an identity matrix of order n. For example, what is I2? I2 is just this 0, 1. I3 is just 1, 0, 0, 0, 1, 0, 0, 0, 1. That's those are identity matrix. So they are just diagonal matrices, but all diagonal elements are 0. So these definitions are so many. We will just define them, just understand the matrix, and then so that next time now we start systems of linear equations. So we are winding up just remaining with a few definitions. What is an upper triangular matrix? We can define what's a triangular matrix, right, in general, but so let us just separate them just for one. What's a triangular matrix? No, what's an upper triangular matrix? Any trial? What's an upper triangular matrix? So a matrix A is said to be upper triangular if Ai is equal to 0 for all I greater than j. And what does it mean? Can somebody tell us this in layman language? What does it mean? Aij is equal to 0 for all I greater than j. In layman terms, what does it mean? So it basically means all elements below the main diagonal are all zeros or are zeros. So you'll have A11, A12, A13, for example. Then all these are zeros. A22, A23. Then this is 0. Then A33. So all elements below the main diagonal are zeros. That's an upper triangular matrix. And then a lower triangular matrix. Is it 6 or 7? 7. A lower triangular matrix. So it's just the opposite of this. Is a matrix A such that Aij is equal to 0 for all I less than j, or for all j greater than I. That means it's a matrix whose elements above the mid diagonal are zeros. That's now an upper triangular matrix. And some of these are important because when you want to solve the system of equations, we will reduce this system into an equivalent upper triangular matrix. And I'm using the word equivalent upper triangular matrix. Or in general, if it's not a square matrix, then this call is what? Is called the row echelon form. So I think maybe you might have looked at this somewhere in linear algebra. What's a row echelon form of a matrix? So it's just basically the generalization of an upper triangular matrix. This upper triangle only occurs if it's a square. If it's not a square, then you get what's called the row echelon form of a matrix. And also remember that by saying that it's an upper triangular matrix, then I don't restrict what happens on the other side. What I know is this has to be 0. This can take any other value. They can be zeros as well. For example, if I have the diagonal matrix, is both an upper triangular and a lower triangle. So that also gives you another definition of a diagonal matrix. That so it's a matrix such that it's both an upper and lower triangle. Then last thing we need to look at is the transpose. But this one you know is the transpose of a matrix A is just a matrix obtained by interchanging the rows of A with columns. Just you swap the rows and the columns. That's the transpose matrix. So A transpose is simply B if A ij is equal to B ji is, so you swap. So when you swap this element, so when you say that B A transpose is equal to B, it means the rows of A are the columns of B. So you are just interchanging rows with columns. That's basically what you need. So having seen at least some understanding or some definitions of a matrix, then we can now proceed to look at systems of linear equations. Then we look at these systems, all the methods, the Gaussian elimination method, the Gauss-Jordan elimination method, the iterative methods, and then later on now try to see how these methods can be used to determine the determinant of a matrix, can help us find the inverse of a matrix, and so on. So, any comment? Any question from you? So should we stop here? Do you want us to continue?
We can continue next time.
What is next time?
You stop. It's
Every
another
day
way
is
of saying it.
every day is a next time. Bado mmelala kwa?
We have a physical class at 10 a.m. and it takes some time.
Okay, yeah,
Transition.
yeah, sure. I understand. Yeah, so basically, it means we will be finishing. We'll be aiming to finish the class 15 minutes, right?
Maybe you can start a bit earlier if the people agree to that.
Yeah, that's what I mean. So the aim is, I give you 15 minutes for changeover to go to the other class, so you leave at 15. And so now it's upon you. At least you should make sure that you come early enough. Ndio tusikuwe tunachelewa. And then basi waambie watu wako wakuje klasi. Waambie sisi sitakangi watu wenye wakuje klasi. So we are 57. So waanze waambie kwamba wakuje klasi. Otherwise I'll be recording I can still record the attendance. So this is the screenshot. I just copy all these names. I can copy all these things at the same time. So waambie wakuje wasome. Wasikae nyumbani. So any other question?
All right. I'll communicate. I will communicate to the student. Next time, expect a bigger number.
Okay. Tuko hapa kwa ajili yao. Sasa waambie wakuje. Wasiache tukule pesa ya bure ambayo itafanya kazi. But so if there are no questions, we call it a day. So see you next week.